In the last lecture, we were discussing the Fourier transforms of functions of time, which are not absolutely integrable over the infinite range. To do this, we laid down certain formulas. These formulas can be justified on the basis of distribution theory. And we will just assume these formulas in deriving these Fourier transforms of these special functions. Special in the sense that x of t is not absolutely integrable. So in such a case, how do we find the Fourier transform of such a function? Okay. So x of t is not absolutely integrable over the infinite range minus infinity to plus infinity. Now to start with, we took the case of a pure DC. Pure DC means the voltage is constant over the infinite duration, let's say t, and this voltage is V volts, and let me denote this guy by x of t, or let me say this V is equal to 1 volt. Now if you take mathematically, this x of t is equal to 1 volt. Now the Fourier transform of this 1 volt would be like you have an impulse, and the impulse strength is 2 pi times del of omega, where omega is equal to 0 and this is your omega axis. The Fourier spectrum will comprise just a single impulse at the origin, omega equals 0 on the omega axis. Okay, so since this time function DC signal time function is a pure DC. If I say pure DC, we cannot expect to have frequencies at any value other than omega equals 0. Pure DC means there is no frequency, so omega equals 0 in this case. That is why you have an impulse which is sitting at omega equals 0. So you don't have any other component, and at that point you have a definite non-zero coefficient in the Fourier transform of f of t, and consequently you have Fourier coefficient density which is infinitely large. Okay. Now let us extend this to a sinusoid. Suppose my signal x of t is equal to cos omega ct. Now I can write this cos omega ct as e to the j omega ct by 2 plus e to the minus j omega ct over 2. In other words, x of t consists of two exponentials. Okay, two exponential functions, 1 by 2 multiplied by e to the j omega ct, or I can write like this, plus 1 by 2 e to the minus j omega ct. And another one is one function is like 1 by 2 multiplied by e to the j omega ct, and another one is 1 over 2 e to the minus j omega ct. Now the difference between 1 over 2 e to the j omega ct and the previous example we had x of t is equal to 1 is that it is scaled down by 1 by 2. Like if you have 1 by 2, that 1 by 2 is scaled down by, sorry, this is 1, and that 1 is scaled down by this 1 by 2, but the time function is multiplied by e to the j omega ct, an exponent. Okay, so recall the property which we discussed earlier. If you have x of t and this x of t take Fourier transform, then you will get x of j omega, then multiply x of t by e to the some exponent e to the j omega ct, then the Fourier transform will be x of j times omega minus omega c. Right. Now instead of x of t I have 1, I have 1 by 2 e to the j omega ct. Therefore its Fourier transform will be 1 by 2, then, or else let me write one more steps, one more step. Now if we take 1, its Fourier transform will be 2 pi times del of omega. Now this 1 is multiplied by e to the j omega ct. Therefore 2 pi times del of omega minus omega c. Now instead of 1 by 2 I multiply by, instead of 1 I multiply by 1 over 2, then e to the j omega ct. The same time constant appears in the output also. So 1 over times 2 pi times del of omega minus omega c. So this is pi times del of omega minus omega c. Therefore the Fourier transform of 1 over 2 e to the j omega ct is pi times del of omega minus omega c, and 1 over 2 e to the minus j omega ct has Fourier transform pi times del of omega plus omega c. Hence x of t is equal to cos omega ct, which we can write, which we wrote as 1 by 2 e to the j omega ct plus 1 over 2 e, minus j omega ct. Okay. So if you take Fourier transform of this, then pi times del of omega minus omega c plus pi times del of omega plus omega c. That's it. Now what do we have? We have two impulses. Okay, first impulse and the second impulse. So in the time domain we have a pure sinusoidal function like this. Let's say this is my sin omega ct, and in the frequency domain I have impulse function. One impulse with a strength of pi and sitting at omega is equal to omega c, and another impulse which is sitting at omega is equal to minus omega c, and the magnitude is again pi. So this is the Fourier transform of my signal x of t. Okay, that means what, it has only one frequency component. That frequency component is sitting here at omega equals omega c. Okay, so what we observe here is, once again, this has only single frequency. It does not have many frequency. It has only single frequency. Therefore the energy is centered or concentrated only at two discrete frequencies, omega c and minus omega c. So this is quite revealing that even a pure sinusoid or a pure DC can be represented by means of Fourier transform in this manner. Now let us extend this idea further. Now let me consider x of t is equal to sin omega ct. So sin omega ct you can write e to the j omega ct minus e to the minus j omega ct divided by 2j. Now the same rule what we said for the previous case we can apply here. So 1 over 2j times 2 pi del of omega minus omega c minus 1 over 2j times 2 pi times del of omega plus omega c. Now 2 will get cancelled and j comes to the numerator, or you can put simply pi over j del of omega minus omega c minus del of omega plus omega c. So this is a Fourier transform of your sinusoidal function. This is cos, right? So I'm sorry, cos omega ct, and in this case it is sinusoidal frequency like this, the time domain. But if you plot in the frequency domain, you have one component at omega c, but the strength is pi over j, and another one is minus pi over j. This is your x of j omega. Now this x of j omega is complex, so you can plot magnitude and phase. The magnitude will be pi, and here also it is pi at omega equals omega c and omega equals minus omega c. This is your magnitude plot. What about the phase plot? Here you have the phase angle of minus 90 degree, and this guy has a phase angle of plus 90 degree at omega equals minus omega c, and this is omega equals plus omega c. This is your phase angle of x of j omega, and this is omega. That's it. Okay, and this one is called phase spectrum. Okay, so now we have found out the Fourier transform of a DC signal and a pure sinusoidal signal, that is cos omega ct and sin omega ct. One can as well go to the extreme case of non-sinusoidal function, and indeed it can be shown that a non-sinusoidal periodic function which admits the Fourier series can also be or can also have a corresponding Fourier transforms. Okay, even you can find a Fourier transform, find Fourier transform for a periodic signal, general periodic signal, not necessarily a sinusoidal signal. Okay, when I say periodic signal, it can be sin omega ct or cos omega ct or any periodic signal. Now let us see how it goes. So Fourier transform of a general periodic function. Suppose x of t is a periodic function. Periodic function which admits the Fourier series representation in the following manner. That is, in that we already done this. We have done that. Sigma n equals minus infinity to plus infinity, then Cn e to the j times n omega naught t. So this is the representation for periodic signal in the complex exponential Fourier series form. So this periodic function is something which repeat itself at regular intervals with a time period t naught. Let's say I have a triangular function like this. Periodically it repeats like this. Whenever you have it periodic function like this, then this function you can represent in this form, exponential Fourier series, where omega naught is the fundamental frequency. This we have already seen, fundamental frequency. Okay, now we have seen that a constant will have a Fourier transform which is 2 pi del of omega times that constant. Suppose we have constant 1, if we take Fourier transform 2 pi times del of omega. Now instead of 1 I have some constant value, let's say c. Then what is the Fourier transform of this guy? 2 pi times c times del of omega. Okay, now if you look at this guy, what is your Fourier series? X of t is equal to Cn e to the jn omega naught t, right? Now where n equals minus infinity to plus infinity, what is this Cn? Cn is a constant here, it is a coefficient, right? So if you take the Fourier transform of Cn, then what will you have? just now we said like if you take one Fourier transform 2 pi times del of omega, then if you take some constant times 1, then it is c times 2 pi times del of omega. Cn times, if you take Cn Fourier transform, this Cn, that this is 1, then Cn times 2 pi times del of omega. Now that Cn is multiplied by an exponent, therefore Cn times, it is frequency shifting, okay, En j and omega naught. If you take Fourier transform, then this constant as it is, then 2 pi times del of omega minus n omega naught, that's all. Okay, so in this expression, each terms in the Fourier series, this is a Fourier series by way, okay, each terms in the Fourier series expansion will therefore have a corresponding Fourier transform. So I have infinite number of Fourier transforms here. I don't have only one Fourier transform. Each component C0 has its Fourier transform, then C1 has its Fourier transform, C2 has its Fourier transform, and so on and so forth. That means what? When you substitute n equals 0, then what will happen? C0. If you take Fourier transform, C0 times 2 pi del of omega. When you substitute c equals 1, then C1 times e to the j omega naught t. You take Fourier transform, then it becomes C1 times 2 pi del of omega minus omega naught. Substitute n equals 2, then C2 times e to the j 2 omega naught, and then it becomes C2 times 2 pi times del of omega minus 2 omega naught, and so on so forth. In case if we substitute n equals 3, then C3 times e to the j 3 omega naught, and then becomes C3 2 pi times del of omega minus 3 omega naught. Similarly, substitute n equals minus 1, then C minus 1 times e to the minus j omega naught t, then it becomes C suffix minus 1 2 pi times del of omega plus omega naught. Substitute n equals minus 2, C minus 2 e to the minus j 2 omega naught t, it has Fourier transform of C suffix minus 2 2 pi times del of omega plus 2 omega naught, and so on so forth. Therefore, each term in the Fourier series has corresponding Fourier transform. So how many terms in this Fourier series? I have infinite number of terms. Okay, each guy has its own Fourier transform. Okay, and the summation of all these transforms of individual components will be the Fourier transform of entire function. So x of t is sigma n is equal to minus infinity to plus infinity, then Cn e to the j n omega naught t, then you take Fourier transform, on the left hand side it becomes x of j omega, the right hand side same summation. Each term has its own transform 2 pi times del of omega minus n omega naught. So based on the n value, you keep on multiplying. Okay, so a periodic function of time which has Fourier series and it has corresponding Fourier transform. Now the magnitude spectrum of this this guy will be like this. When n equals 0, you will get the maximum magnitude 2 times 2 pi times C naught. When n equals 1, 2 pi times C1. When n equals 2, 2 pi times C2, and so on so forth. And this side also it will be 2 pi times C suffix minus 1. When n equals 2, 2 pi times C minus 2. That means what? The C0, C1 are Fourier series coefficients. Yes or no? So C0, C1, C suffix minus 1, C2, C suffix minus 2, dot dot dot. This all are what? Fourier series coefficients. Now if you want to find out the Fourier transform, then the magnitude plot will contain the coefficients will be multiplied by 2 pi, and this guy also multiplied by 2 pi. So all are multiplied by 2 pi. So this is the magnitude plot x of j omega. So if you plot the spectrum of the Fourier series in a conventional sense, would be a line spectrum. So this has a special name called line spectrum, because the spectrum looks like a line. In between you don't have you don't have any spectrum, no spectrum. So we have spectrum only at integer values of omega. Integer values of omega naught, I am sorry. This is 1 and this is 2 and so on. And the gap between these two guys is omega naught. And this is omega naught. And this also omega naught. And so on so forth. So this gap is going to be 2 omega naught. Minus 1, minus 2 and so on. Okay, so you have magnitude spectrum of Fourier transform, as well as you can have magnitude spectrum of Fourier series. Suppose if you want to find out magnitude spectrum of Fourier series, then this is going to be C naught, then C1, C2 and so on, and this side it is C minus 1, C minus 2. The only change is you multiply by what? 2 pi. Okay, now what we have in the case of Fourier transform is, instead of these coefficients, we have impulses. Okay, here these all are coefficients, and here these are all impulses. Okay, so instead of finite constant here C1, C2, C0 like that, the strength of each coefficient is multiplied by 2 pi, and this also multiplied by 2 pi, this are also multiplied by 2 pi in the Fourier transform. So we have seen that the Fourier integral gives a more generalized concept of finding out the various harmonic components of a function of time. It can be used not only for a periodic function, but also Fourier transform can be used a periodic function. Okay, because once you have the Fourier series for a periodic function in the Fourier transform domain, all it means is the same line spectrum. See, these two spectrums are same line spectrum. The Fourier transform also line spectrum, Fourier series also line spectrum. Okay, so same line spectrum carried over into the transform domain as well. But instead of finite valued coefficients, here this all are finite valued coefficients. C naught, C suffix minus 1, this all are finite valued coefficients. So instead of finite valued coefficients in Fourier series, in Fourier transform we have an impulses. Okay, so you have impulses, and each of which has a strength proportional to the Fourier coefficients, that is Cn. Now it is a continuous spectrum because it is not a continuous spectrum. Okay, so these all are discrete spectrum. So the important point is, if x of t is aperiodic, then x of j omega will be a continuous spectrum. Okay, if x of t is periodic, then you can, whenever it is periodic, then you can use Fourier series. Because of the Fourier series, you have Fourier series representation. Let's say x of t is equal to sigma n is equal to minus infinity to plus infinity Cn e to the jn omega naught t, and from where if you take again Fourier transform, then you will get a discrete spectrum. Or line spectrum. So, if the signal is aperiodic, then it is a continuous spectrum. If the signal is periodic, first you take the Fourier transform, and then for each coefficient you take the Fourier transform, you will end up with a line spectrum or discrete spectrum. Okay. So, the conclusion that we get is whenever you have a periodic function of time, then the spectrum will turn out to be a line spectrum. Similarly, whenever you have a aperiodic function, the spectrum turns out to be a continuous spectrum. Okay, so let me stop at this point. In the next lecture, we will talk about the transform of or Fourier transform of a unit step function u of t. Okay, so let me stop at this point. Thank you very much.